Hello. We're going to do a conservation of momentum problem applying Newton's laws of motion relative to forces in two dimensions. In a train yard, train cars are rolled down a long hill in order to link them up with other cars as shown. A car of mass 4,000 kilograms starts to roll from rest at the top of a hill 5 meters high and inclined at an angle of 5 degrees to the horizontal. The coefficient of rolling friction, or the coefficient of kinetic friction, same thing, between the train and the track is 0.05. What velocity would the car have if it linked up with three identical cars sitting on flat ground at the bottom of the track? The initial momentum will equal the final momentum. We need to determine two things: the velocity of the 4,000 kilogram car rolling down the ramp, and then after it couples with the other three cars, now the new larger train will have four identical cars. What will that velocity be? Now, if we expand the row to include MV, MV initial will equal MV final for the system. The initial mass will be 4,000 kilograms. That will be the mass of the single car. And then after that single car collides with the other three, then the single moving mass will be 4 times 4,000, or 16,000 kilograms. Everything listed in the table is what is given and what needs to be calculated. MI, or M initial, is 4,000 kilograms. That's the mass of the train on the ramp. dy is the height of the ramp, or 5 meters. Theta, the angle, is 5 degrees. The coefficient of friction is going to be 0.05. The dH would be the length of the ramp. Fw would be the weight of the car on the ramp, or mg, relative to 4,000 kilograms. Fn is that weight which is perpendicular to the ramp. Fp is that weight which is parallel to the ramp. Ff is friction. Fnet is the net force. A will be the acceleration of the train down the ramp. V before will be the velocity the train achieves just before collision. Mf is 16,000 kilograms. That will be the mass of the four train cars after coupling. And V after, final, will be the velocity of the train after it collides and couples with the other three trains. The first value that we'll calculate is the length of the ramp, or dH. dH equals dy over sine theta, or 5 meters over sine 5 degrees, and that's going to equal 57.4 meters. Please verify trigonometrically that that is true, and verify it also on your calculator to make sure you get 57.4 meters, which is the distance the train will travel to pick up a velocity before colliding with the other three cars. That value is written in the table. dH equals 57.4 meters. The next value to calculate will be the weight of the car. The weight of the train car, it should be easy to calculate. Fw is mg. It would be 4,000 times 10 meters per second squared. The next value to calculate would be Fn, or that part of the weight that is perpendicular to the ramp. and that would be 40,000 newtons times cosine 5 degrees, or 39,847.8 newtons. We see Fn is written in. The next value to calculate is Fp. Remember, with Fp and Ff, remember to consider the free body diagram as to what will be the sign or direction of each Fp and Ff. Fp equals 40,000 newtons sine 5 degrees, which equals a positive 3,486.2 newtons, because it's positive, because it is in the direction of the motion. Here we see that is written in the table, and the next value that we want to calculate is the friction. The friction is simply the product of mu times Fn, and it will be negative because it is contrary to the direction of the motion. It is a resistance. It is negative 1,992.4 newtons. The friction is written in the table as negative 1992.4 newtons. The next value to calculate would be the F net of the train car. The F net of the train car would be the sum of Fp and Ff. Remember that Fp is positive, Ff is negative, Fp is larger, therefore F net will be a positive 1,493.8 newtons. F net is written in as positive 1,493.8 newtons. The next value we have to calculate is the acceleration of the train car as it is coming down the ramp. Remember that acceleration is a quotient, a ratio of net force over mass, positive 1,493.8 newtons divided by 4,000 kilograms. Make sure you verify this value in your calculators before proceeding. Positive 0.373 meters per second squared. The acceleration is written in. Note that it is a positive 0.373 meters per second squared. The next value we're going to be calculating is the velocity the train car achieves as it accelerates 0.373 meters per second squared before it couples with the other cars. We calculate the velocity of the train car just before it couples at the bottom of the ramp by using the equation, a modified version of the equation, Vf squared equals V naught squared plus 2AD. V naught is 0, therefore V final or Vf squared equals 2AD, where V final will equal root 2AD. V final is actually V before, which is the velocity the lone car achieves at the bottom of the ramp just before coupling. A very, very important value. Make sure that you verify this value, that you understand where the equation comes from, you understand where the numbers in the equation come from, and you have again verified that value on your calculator before you proceed. To calculate the final velocity of the system, you have to note that the total initial momentum will equal the total final momentum. M initial is 4,000, M final is 16,000 kilograms respectively. The velocity before the collision is 6.54. In order to calculate the velocity after the collision, we set the equation up as shown. 4,000 times 6.54 divided by 16,000 will equal 1.64 meters per second. Now, it's important for you to verify that the left side equals the right side. The whole point of the problem is that the initial momentum will equal the final momentum. So the final velocity of the cars, the 4 cars after the coupling, will be 1.64 meters per second. The final velocity of the system is written in as plus 1.64 meters per second, and that concludes the problem. Have a great day, and goodbye.